Okay, hello everyone. Welcome back to these tutorial videos on theory of computation. So in this video, we'll be doing something that I think and I hope will be fun for you. We'll actually be sort of looking at an algorithm that can be used to parse to generate the parse trees for a complex-free grammar in Chomsky grammar form, given a string, an input string. Okay, so we're going to look at a parsing algorithm basically. So today we'll be looking at a parsing algorithm, which is known as the um, Koch, Younger, and Kasami algorithm. So it's usually called the CYK or the CKY, or uh, for some reason the C is always first, but sometimes it's CKY, sometimes it's CYK algorithm. So this is how most people call it. Like I said in a previous video, I actually call it the CKYS algorithm because it was actually discovered by a fellow by the name of uh, Itiru, um, Itiru Sakai in 1961. Okay, so Koch, Younger, and Kasami, they actually rediscover the algorithm. So this poor Itiru Sakai fellow, he didn't even get a letter of his name in the algorithm, even though he discovered it. So there's probably a life lesson in there, but I can't really think of it. Okay, but anyway, the CYKS algorithm, what the CYKS algorithm does is it's given a grammar, right? And it's given a string, and what it does is it's sort of a decision procedure, right? It's an algorithm that gives you an answer yes, no, where um, it says no if W is not generated by G, and it says yes if W is generated by G. But the bonus is that to actually determine that, it also at the same time finds the parse trees for that string. Let's find the parse trees. And it does this just because it just so happens that in the algorithm, you're determining whether there are parse trees for that string to check whether it's generated by the grammar. And so like a side effect is that you also get parse trees, which is nice because it allows you to sort of interpret the meaning, right, of a string if you're talking about sort of linguistics, or if you're talking about a programming language, you can sort of see how operations sort of connect together in the parse tree. And the reason why I'm talking about this algorithm after we've done the simplification videos and the CNF video is because the Chomsky normal form, the fact that you can get a grammar in Chomsky normal form, is essential to this algorithm, for this algorithm, excuse me, to work. Otherwise, the algorithm would become sort of exponential in nature. Like you could sort of brute force this algorithm, but it would be you could brute force a parsing algorithm, but it would become exponential. This algorithm is actually O length of W cubed, which is actually relatively fast, given that the other best thing you could do is something exponential. Okay, and so like I was saying, the the fact that you can get a grammar G into CNF allows you to get this sort of speed up because you can actually use a dynamic programming sort of table-based method. Um, right, so like I just said, in the CYKS algorithm, you either assume G is in CNF, or you have a sub procedure, or you have a subroutine, which converts G to G prime in CNF, right? Okay. So how does this algorithm work? It essentially relies on the fact that now if my grammar is in CNF, all I really have basically is a binary parse tree, right? So if I have some string, like if I have some string, let's say A, B, B, A, B, right? Then I know that my parse tree is going to start with S, right? And from S, I can only have sort of binary branches, right? Binary um, sort of production rules, right? So only two sort of children from the start variable S. So what that tells me is that if this is my sort of finalized string, then there's actually a finite number of ways to derive that string, right? Even without just thinking about the production rules, there's a finite way of deriving strings like this, right? Either S could have given you some variable, let's call it A, and then A could have derived this terminal A, and then the rest, B, would have derived this other sort of part of the string, right? Where you have a subtree. So here you have some kind of subtree, right? So that's one possibility. Another possibility is, maybe you derived a variable A, which which sort of creates a subtree that gives you AB, and the other rule, the other variable B, allows you to derive this other subtree, right? And you can hopefully see where I'm going with this. There's only sort of, in this case, one, two, three, four ways of doing this, right? So there's four sort of ways of splitting this string A, B, B, A, B, right? So, the other way would be, let me just use the highlighter in this case. A would go here, and then B would go here. And then lastly, there would be A covers everything except the last string, and B covers the last, everything except the last terminal, and B covers the last term, right? And so you're probably still thinking, well, where does the dynamic programming come in? Because dynamic programming typically requires sort of a recursive step, right? So where's the recursion here? Well, the recursion is just that, once I apply this to the entire string, then I sort of recurse on my substrings, right? So I apply the same procedure of finding the correct parse tree, but for this substring, and then do the same thing for this substring, right? So like for instance, in the case where this was in the case where this was the correct or one of the correct, because there could be more than one, right? The grammar could be ambiguous, but this was one of the correct production rules to get me started, to get this this final string. Then for the parse tree with B, then there's a few possibilities again, right? There's, I could have B gives me some variable C and D, where C covers B and D covers AB. Or there's also the possibility of C covering BA and D covering B. Okay, so you can see there's sort of, if this was a subroutine, right, you would just be recalling the subroutine on the variable B, right, on the tree rooted at B rather than S. Okay. And so you keep doing this, right? You keep doing this until you get terminals, and then that creates the parse tree, right? But now to do dynamic programming, right? To do dynamic programming, one typical approach, right? There's sort of the bottom-up table approach, and then there's the memorization approach. In this case, if you use the bottom-up approach, then what you need to do is you sort of have to do this sort of backwards, right? So you account for all the ways to derive sort of each of these terminals, right? And then you say for each of the ways of deriving terminals, like for instance, if I had a variable A here, had a variable B here, something like this, then you would say, well, is it possible for me to derive, say, AB from a rule, and then, yeah, is it possible for me to have some variables, let's call it F, that derives this rule, where this is the rest of the parse tree, right? And then I would do the same operation on the other parse tree, where I say, well, can I derive sort of CDE with maybe some some production rule CDE with some production rule that looks like, you know, B and then E, and then B gives me C and D, right? Something like that, right? So the logic that I described was top down, but really what you're doing is you're going bottom up, okay? So that's like the intuitive. I'm not going to write out the actual procedure, but that's the sort of intuitive way of thinking about how to run it. I'm actually just going to give you an example, and hopefully that will make things a bit clearer. Because like in most of the algorithms I've presented, it's pretty hand wavy at this point. Okay, so consider the context-free grammar G in Chomsky normal form, where G has three variables. The production rules for each of the variables are the following. Okay. And I want to run CYKS. I want to run CYKS on the string. Let's keep things simple, A, B, B. Okay. So, right, so I want to sort of try to do this bottom-up approach. And so how do I do this? Okay. So let's start by writing the string A, B, B here. Okay. And now what I need to do is the first step, I need to account for all the ways of generating the terminals, right? So what is a way to generate the terminal A? Well, that's using A gives you A and B gives you A, right? So notice why Chomsky normal form is so important, because in Chomsky normal form, the only production rules that give you terminals, right, are of the form, just the variable and then just the terminal, right? So you know that you don't have to deal with like, oh, well, maybe you have to consider A and then with B, right? So you don't have to consider the context of the input, right? Because if you had to do that, then it would be very hard to sort of do an elegant sort of bottom-up approach. Okay, so what are the ways of deriving A directly? That's with the variable A, and then also with the variable B, right? So I have to account for both possibilities. Then what are the ways of deriving the variable, the terminal B? There's only one way, right? With the variable A. So in this case, there's two variable A's, right? Okay, and now here's where it gets a bit tricky. Right now, I have to sort of consider, well, maybe I have, right, maybe the split is here. Maybe my split for my parse tree is here. And so then I have, from S, I have some way to get to A, and then some other way to get to AA, right? So that's one possibility. The other possibility is if I'm here, I have some way to get to, AA, right? AA or BA, right? And then I have another way of getting to just A, right? So I have to try both of these cases, right? I have to try both of these splits. So split one would be, can I do something like do I have a rule that's like something like S gives me A, and then S gives me something else? And do I have another rule that gives me something like S gives me B, and then S gives me something else, right? Because then I just have to check whether this rule here gives me AA, right? So that's the first thing I need to check for. That's the first thing I have to check for one of the possible splits. The other possible split would be, can I from S derive A on the right, and then can I derive the sort of rest of the parse tree, so either AA or BA, right? So then we just have to check that, right? So we look at our rules. If we look at our rules, I have 4S. I have 4S. Just S gives me AB, right? Just S gives me AB. So that tells me that this production rule, like this possibility is already eliminated because it would have to start with a B. And this one is also eliminated because it would have to end with an A. So the only possibility is if I had S gives me A and then something, right? Where now I know that that something has to be A, right? So now I check, well, do I have a way of deriving AA? I do, right? I do, well, using B, of course, right? I do, right? I have B gives me AA, right? So, right, I said the only possibility is S gives me A and then B. And then I check, well, can I derive AA with B? Yes, I can, right? So then the parse tree and it looks like the only parse tree that allows me to do that is if I say S gives me uh, A and then S gives me B, then B is A and then A. Okay. And so um, and so this is how you sort of run um, the CYKS algorithm. So you could just imagine that if you had more layers, then you would be accounting for more of the possibilities, right? Like if you had an extra terminal here, if you had an extra terminal here, then you would have to account for one possibility where you try to derive this thing, and then a second possibility where you try to derive this thing, and then a third possibility where you try to derive this thing, right? Um, and then right, so then within each of the subtrees, you just have to rerun this sort of check that I'm doing right now. Okay. So this is to give you a general idea of how the CYKS algorithm works. It's not a super formal presentation, but hopefully it gives you a general idea. I'm sort of just trying to show you that intuitively this kind of makes sense. Um, Okay, so that was basically it. I just wanted to do this extra video just to show you that, like I said, initially CNF is actually quite important. So we're not just doing simplification and converting to CNF just for the sake of doing that. There's actually very real use cases of CNF. The other one is the proof for the pumping lemma for context-free languages. So that requires that your grammar is in CNF so that you can sort of show that you can pump up some part of the parse tree. Okay. Okay, so I hope this was more or less interesting. And yeah, see you in the next video.